This is the demo for lesson 32 in college algebra. Number 1, just a little reminder, an exponential function has the formula f of t equals a times b to the t. A can't be 0, or else this would just be a function f of t equals 0. B has to be positive, and b can't be 1. A is your initial value, the value of your function at t equals 0. B is called the base, also called the growth or decay factor. And b is 1 plus r. R is the growth rate or decay rate written as a decimal. If there's exponential growth, then r is positive and b is bigger than 1. And when you have exponential decay, r is negative and b is smaller than 1. And r is often referred to as the periodic growth rate. You might see that in your homework. So here are some examples of exponential functions: 10 to the t, 5 to the t, 3 to the t. E to the t is also called the natural exponential function, and we discussed e in a previous lesson. And then we have 2 to the t and 1.5 to the t. So you can see that as the bases, as the value of the base increases, the function gets steeper. It grows faster and faster. And these all represent exponential growth. And then these functions, I have 0.1 to the t, 1/2 to the t, 0.8 to the t, 0.9 to the t, 0.95 to the t. These all represent exponential decay because the function is decreasing. And the smaller the base, the faster it decreases. So exponential functions are used to model population growth, radioactive decay, compound interest, biology, sales, many other applications. A commonly used base is the number e. Exponential growth models come in two equivalent forms. A of t equals a naught times b to the t, and a of t equals a naught times e to the kt. So a naught is the same in both functions. A naught represents the initial quantity at time t equals 0 in both formats. Okay. In this format, a naught times b to the t, b is the growth factor when b is bigger than 1. And if you want to know the decay rate or the growth rate, you do b minus 1, and that will give you the percent growth or decay rate. A naught equals e to the kt. This is an exponential function with a base e. It's called a continuous growth model. So if you see the word continuous in a homework problem or test problem, you might want to, it will be easier to use this model than to use this model. Okay, so that word continuous is very key. A naught represents your initial quantity, just like it does over here. And k is called the continuous growth rate when k is positive. Okay. So these two equations are equivalent, and to make them, for them to be equivalent, b has to be the same thing as e to the k. b equals e to the k, and if you wanted to solve this equation for k, you could take the ln of both sides, and you would have k is equal to the ln of b. So these two equations are how you convert between these two forms. So number 3, we had an Ebola outbreak in West Africa in 2014. On September 3rd, there were an estimated 3,902 cases. And between September 3rd and November 18th, the number of Ebola cases grew at a continuous growth rate. Continuous, keyword continuous. We're going to use this format, at least to start, okay, of 1.252%. Okay, so I'm going to construct two equivalent models, one just a standard exponential growth model, and the other an exponential continuous growth model. So I'm going to do the continuous one first because they gave me something about the continuous growth rate. They gave me k. So I'm going to start with a of t equals a naught times e to the kt. And then I'm going to plug in the things that they told me. The initial number of cases will be 3,902. That's the first recorded number that we have. And then e is a number. It's like 2.718. K is my continuous growth rate. I'm going to put that in as a decimal. So this is going to be 0.01252 to the t. Okay, so there is my continuous growth model. And then to write the equivalent exponential growth model, I just need to figure out what b is, and I have a formula for that. B is e to the k. So I'm going to use my calculator. B equals e to the k, which is e to the 0.01252, and that will come out to approximately 1.0126. Okay, it's approximate because e is an irrational number. It will never give you a perfect decimal when we use an e. But I can now write my equivalent formula, A of t equals A naught, which is the same as the other model, 3902, times b, which is 1.0126 to the t. Okay, November 18th represents day 83 of the outbreak. How many Ebola cases does this model predict for day 100, December 5th? So I'm going to use each of the two models and get a prediction for day 100. So A of 100 will be 3902 times 1.0126 to the 100. And that comes out to 13,648. We'll just round to the nearest whole number because it's number of cases, so we'll just leave it there. We're going to do the same process using our equivalent model. So A of 100 should be 3902 times e to the 0.01252 times 100. And that comes out to 13,646 cases. Okay, so these two models are equivalent. These numbers should be the same. Okay, they are very, very close. The only reason they're different is because this 1.0126, that was approximate. If I had kept more decimal places when I calculated this approximation, these would be even closer. Exponential decay models also come in two equivalent forms, A naught times b to the t. Again, A naught is our initial quantity. B is our decay factor. It will be less than 1. And R is b minus 1, and that is our decay rate. And then A naught e to the kt, this is called a continuous exponential model. A naught is the initial quantity. K is the continuous decay rate, and K will be negative. And then we have the same two equations to convert between the two models. Okay, B equals e to the K, and K equals ln B. So an example of exponential decay is half-life. Okay, so the half-life of a substance is the length of time required for 1/2 of the current amount of the material to decay, and is an example of exponential decay. Radiocarbon dating is an example of this. So how can we approximate the date a plant or an animal died? Scientists use radioactive carbon-14, which is found in all living things, to estimate the age of fossils, artifacts, paintings, etc. So C14 has a half-life of approximately 5,730 years. That means that if whatever amount of C14 you start with, you'll have half of it after 5,730 years, and then it will have again in another 5,730 years. So carbon-14 dating can be used on objects that may be up to 80,000 years old. I want to find the continuous decay rate K of carbon-14 and construct the exponential decay model, the continuous exponential decay model. So I'm going to start working with this model, the A naught times b to the t, because what they've given me is half-life. So I'm halving the amount of stuff that I started with every 5,730 years. So my base B is going to be a half, right? I take A naught, my original quantity, I multiply it by a half some number of times. Okay, so I'm going to say A of t is A naught, they didn't tell me how much I'm starting with, times 1/2 And then I multiply by a half some number of times, and the number of times I have my original quantity depends on how many sets of 5,730 years have gone by. If exactly 5,730 years have gone by, this would be the first power. I would do a naught times a half once, because we have every 5,730 years. If 5,730 years has gone by twice, that means 11,460 years, then I would square this, right? I would say I'm going to have my original quantity twice. So what I need to know, I need to take the number of years and divide by 5,730. That'll tell me how many times to have my initial quantity. So I'm going to say take whatever the number of years is, t, and divide it by 5,730. That tells me how many sets of 5,730 years have gone by and how many times I should have the initial quantity. So this is a format for carbon-14 dating using a naught times b to the t. So now from here, I want to construct the continuous exponential decay model and the continuous decay rate k. So I'm just going to do a little bit of fancy algebra. Okay, so this is the same thing as a naught times 1/2 to the 1 over 5,730 to the t. Okay, because when you raise a power to a power, you would multiply the exponents. So this fraction times t would give you t over 5,730. Now I can say that b, my base of the exponential model, is 1/2 to the 1 over 5,730. And once I know b, I can figure out k. I just take the ln of it. Okay, so k is going to be the ln of 1/2 to the 1 over 5,730. And that comes out to approximately negative 0.000121. Okay, so there's my k value, the continuous decay rate. And then I can use that to build this model, a naught e to the kt. So a of t equals a naught times e to the k, which is negative 0.000121 t. Now I want to use the continuous decay rate that I just found and the following formula to confirm the given half-life. Okay, so I'm going to do the ln of 0.5 divided by k. So the ln of 0.5 divided by k, which I rounded. It's negative 0.00012, and I rounded it to 1 here, but it's really 9688094. I want to get as close as possible as I can to the actual half-life, so I didn't round these. I didn't round this k this time. So this comes out to 5,730, or very close. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? So I have two models for the exponential decay. I have this one, and I have this one. Okay, but this second one has a rounded value for k in it, so I think I'm going to use the original. So I'm just going to write it down. A of t equals a naught times 1/2 to the t over 5,730. Okay, so a bone fragment is found that contains 20% of its original carbon-14. So it has 20% now. How much did it start with? 100%. Okay, its original amount of carbon-14 we can say is 100%. So I'm going to put a 100 in here for a naught times 1/2 to the t over 5,730. And set that equal to 20. When does it have 20%? And I want to solve this equation for t. So I'm going to start by dividing both sides by 100. I'm going to try to isolate the exponential. So I have 0.2 equals 0.5 to the t over 5,730. And then I take the ln of both sides, and that will allow me to bring my exponent down in front. So the ln of 0.2 equals t over 5,730 times the ln of 0.5. And then I'm just going to try to isolate this t. So t will be ln of 0.2 times 5,730 over the ln of 0.5, and that comes out to approximately 13,305 years. Part D is to construct an equivalent exponential decay model. We've already constructed two. So our two equivalent models were A of t equals A naught times 1/2 to the t over 5,730. And then our continuous decay model says that A of t equals A naught e to the negative 0.000121 t. And I rounded that k value a little bit. To summarize, we have two forms of exponential growth or decay. Okay, so A of t equals A naught times b to the t, also called periodic growth. And then I have continuous growth, which is A naught times e to the kt. And then we have formulas that can relate b and r. So b is 1 plus r. The half-life is ln of 0.5 over ln b. And in the continuous model, the half-life is ln of 0.5 divided by k, and k is the ln of 0.5 divided by the half-life. Example of wording to look for: increases at a rate of 7% per hour. R is just 0.07. Okay, so we have a very clear 0.07. And then increases at a continuous rate of 7%. That means we have a k value in this model, 0.07. And there are two equivalent half-life models: initial quantity m naught or A naught times 1/2 to the t over h, or m naught e to the negative kt. And then I list what each of the variables represents. And for these two equations to be equivalent, k is the ln of 2 over h, and h is the ln of 2 over k.